some parameter rho, which I'll take to be positive, but basically everything I say, you can think of it being negative also. And the basic definition is that the Gaussian noise stability of a subset of Rn is just the probability that both of my Gaussian vectors land in that set. And this is a pretty simple notion, but it turns out to be quite useful. So in particular, of relevance to this week, it has applications in approximability and in testing. I'll say a little bit more about the application to testing a bit later. But I mean, these are just some examples. Of course, it's been applied to many other things. Now, the basic question that you can ask about this definition is, what sets have higher noise stability than other sets? And there's a very nice answer to this question due to Borel, which is that of all the sets with a particular volume, half spaces have the largest noise stability. And maybe I'll just go back to the previous slide just for a second for the people that walked in to say what the noise stability is, because otherwise nothing else will make sense. The Gaussian noise stability of a subset of Rn is the probability that two correlated Gaussian vectors both land in the set. Okay, and the theorem is that half spaces have the largest noise stability. So here's the formal statement. Let's take a minute to parse it. So for every subset of Rn, I consider A prime, which is a subset of the same volume, but it's a half space. And then the statement is that the noise stability of A is smaller than the noise stability of A prime. And just to be absolutely clear, what I mean by a half space is a set of this form, x in Rn such that x dot A is less than B, so basically a linear threshold set. Okay. Now, one of the main things that I want to do today is to give you a new proof of this theorem, which is, I think, somewhat simpler than the original proof due to Borel. And then also, one nice thing about the proof is that it's going to give us a little bit more refined information about the inequalities. So in particular, it'll help us to characterize the equality cases and also say a bit about the near equality cases.
I'm sorry, where volume means with respect to this distribution.
Volume means Gaussian, yeah, the Gaussian measure, right? So when I say probability of A, I mean probability that X is in A, or probability that Y is in A, because they have the same distribution. Yeah. I mean, it sort of makes sense to have this restriction because I'm asking, right, if A is a set that X lands in with very high probability, then of course it's going to have a large noise stability by my definition. So. Oh, that's backwards. Okay. Right. So first of all, I just want to restate the theorem in a way that's going to be a little bit more convenient. So I define capital phi to be the usual Gaussian CDF function. So capital phi of x is the probability that a one-dimensional Gaussian is smaller than x. And I'm going to consider this set a lot, the set of x in Rn, such that x1 is smaller than phi inverse of A. And the point of this, right, this is a half space. And it's a half space which is perpendicular to the first coordinate. And this threshold here is chosen so that the half space has volume A. Right? That's what the definition of phi tells me. Okay. And now I'm going to define this function j, which is the probability that first coordinate of x is, so basically the probability that x is in this half space and y is in this half space. Right? And the point of making this definition is that I can restate Borel's inequality in this form. So the point is that the Gaussian measure is rotationally invariant. So instead of just considering any half space, I can rotate my half space and assume that it's perpendicular to the coordinate axis. And once I've done that, then the definition of this function j ensures that this statement is equivalent to the earlier statement. Right? What I've got here on the right-hand side is the noise sensitivity of this particular half space, whose volume is the same as the volume of A. Okay. So I haven't done anything yet, but so these are the new results that I promised. So first of all, okay, so here's my inequality, right? If I have equality, so the first new result is that equality is only achieved for half spaces. Of course, you can change A up to a set of measure 0 and it won't change anything, so equal to a half space up to measure 0. And the next thing is something about almost equality. So I'm going to say, what if I reverse my inequality and add a little bit of slack to the right-hand side? So my set doesn't have optimal noise stability, but it's pretty close. And then it turns out that it must be pretty close to a half space. Okay, so what I mean by pretty close is the Gaussian measure of the symmetric difference is small. On the right-hand side, there's some constant, which depends on the parameter rho and on the measure of the set. And then in terms of delta, it's polynomial in delta. Okay. We give an explicit form for this exponent, but it's not optimal. However, recently there was an improvement to this due to Ronan Eldan, who did two things. So first of all, he got the optimal dependence on rho. This turns out to be the optimal dependence on rho in the constant. And he also got the optimal exponent of delta, which is a half. However, there's still an extra log term there that we don't know if it's necessary. Yes?
So if I have maybe statements like that would be true, that
Yeah, so I could put a b here and a b there and it would still be true. Yeah. So what that's sort of saying is if I want to define my noise sensitivity with two sets, I want to maximize the probability that x is in A and y is in B, then I should take them to be parallel half spaces. And I'm just going to go through the proof for one set, but really the exact same proof works. You just put in a b for half of the things.
Is there also, can you say something if this probability is just greater to some delta? It's only a little noise table? Maybe it has some correlation with half space?
Yeah, that's a good question. I don't know. Yeah, I mean, I think if this is really small, then your set is almost like little bits of stuff everywhere, right? So, right, yeah. Then I don't know. Yeah, that's a good question. We only looked close to the threshold. Okay, so there's a few proofs of this theorem that are known. So there's the original proof, which uses Ehrhart symmetrization in sort of quite a careful way. There's a proof from a few years ago due to Isaacson and Mossel, who sort of translated a result that was due to Burchard and Schmuckenschlager on the sphere and then turned it into a Gaussian result. And more recently, there was a sort of very simple and nice proof due to Kindler and O'Donnell that doesn't quite capture the full generality because it only works for sets of measuring a half and for certain values of rho. And then I'm going to give another one. Okay, but before I give the proof, I want to give a little application to testing. So in this, I'm going to talk about testing Gaussian half spaces. So I'm going to suppose there's some unknown set A in Rn, and we have oracle access to it, so we can query points. And I want to check if A is a half space or close to a half space. So let me sort of mention that really the application is no one really wants to test Gaussian half spaces. You want to test Boolean half spaces. And the problem of testing Boolean half spaces was solved by Matulev, O'Donnell, Rubinstein, and Savidio. But testing Gaussian half spaces is an important first step. And it's sort of easier to talk about. So I'm just going to talk about that. Okay, and now the goal, of course, in testing is I want to give a randomized algorithm, which if A is a half space, it's going to accept with high probability. And if A is far from being a half space, then it's going to reject with high probability. So here's my algorithm. I'm going to sample m points from a Gaussian distribution. And I'm going to take p hat to be my estimator for the volume of A. Okay? Now I'm going to sample m more points, which are pairs of correlated Gaussians. And my criterion for accepting is going to be, I'm going to take this thing, which of course this is just an estimate for the Gaussian noise stability. And I'm going to accept if it's bigger than this threshold, which is like, this is what I expect the noise stability to be. And then I'm going to put a little slack there. Okay. So here's a theorem. Maybe it doesn't deserve to be called a theorem because it's sort of a bit trivial given what I've told you. So first of all, if A is a half space, then this algorithm is going to work, right? And that's obvious because this is what the noise stability should be, and this is my estimate. And if I put a little bit of slack here, and M is large, then it's going to work. Okay. And now the direction which actually requires something is that if A is far from being a half space and M is sufficiently large, then this algorithm is going to say no. Right? And the reason for this is because of the previous theorem. Right? If A is far from a half space, then the contrapositive of the other theorem says that A has low noise sensitivity, or at least far from optimal noise sensitivity. And that means that this quantity, at least the expectation of this quantity, is going to be smaller than this. And so if I take m to be large enough, then it will be, then my sample will also be smaller. So the dependence on epsilon, so this epsilon squared comes from the square root of delta that appeared in the theorem. So if my set is epsilon far from my half space, then it'll have epsilon squared deficiency in the noise sensitivity, and then I have to take m to be epsilon to the minus 4 because 1 over square root of m is the sample error, and that has to be bigger than this. So that's where my dependence on epsilon comes from. And this gives a slight improvement on the result that I told you about before, which required m to be e to the minus 6, and was just a tiny bit more complicated, but not a whole lot. So anyway, that gives an application of our theorem. Okay, so now I'll tell you the proof. Okay, so remember this, I had this function j that I defined, and here's what I'm going to try and prove to you. That for any function, so now I've done something a little bit sneaky here, which is I used to have an inequality about sets, and now I'm changing it into an inequality about functions just because that's going to be easier for me to prove. So for any function from Rn to 0, 1, I claim that the expectation of j, applied to f of x and f of y, is smaller than j of the two expectations. So why does that give you the original statement? Well, you just plug in indicator functions, right? So if I set f to be an indicator function, well, the point is that if you look at what happens when I plug in 1 and 0 to j, right? So phi inverse of 1 is plus infinity, and phi inverse of 0 is minus infinity. So if I plug in 1, 1, then I just get 1. And if I plug in either coordinate to be 0, then I get 0, right? And so what happens here on this left-hand side, if I plug in indicators, is I just get the expectation of 1 on the event that both of these guys land in A, right? So you see that these two are really the same thing. Okay. Right, so there's one more ingredient in the proof. So here's, I've just rewritten the inequality. I'm going to define this funny operator p sub t, or the set of operators, for every t bigger than 0. I have p sub t acting on functions. P sub t of f at x is given by some formula. So the formula is important, but not for today. So I only need to know two things about this formula today. First of all, if I plug in t equals 0, then this term is 1 and this term is 0. And so I've just left with pt of f at x equals f at x, right? And on the other hand, if I plug in t equals infinity, then the other thing happens, right? This is 0 and this is 1. And so I just get a constant function which is equal to the expectation everywhere. So this pt is doing some sort of interpolation from the original function down to a constant function. Okay. Now I'm going to look at this funny quantity for some reason. Expectation of j. So that's like this thing, except instead of f of x and f of y, I'm going to plug in pt of f. Right? And now the point of considering this thing is now if I plug in t equals 0, then I've just got the original thing. And if I plug in t equals infinity, then I've got this thing on the right-hand side. And now the punchline of the proof is that this thing is increasing in t, right? And so then you get the inequality. So let's check that it's increasing in t. I define these v and w, and I'm going to differentiate this quantity. And now the point is that everything's very explicit, right? J is some explicit function that I can write in terms of some integral, and this has an explicit formula, so I can just actually differentiate this quantity, apply the chain rule, integrate by parts, and I get some answer, okay? So what's the point of this answer? Well, this is some non-negative constant. This e to the something is strictly positive, and I've got a norm, so this is non-negative, and that's the proof. Modulo some calculus. Okay. So there's at least two sort of suspicious things in the proof. The first one is I had this thing about sets, and then I changed it into this thing about functions. And it just so happened that the thing about functions that I changed it into had this weird proof where you differentiate in t and something's positive, right? So I want to explain two things. First of all, what does it mean to go from the set statement to the function statement? And secondly, why might you expect this differentiating in t to actually give you anything? Okay, so the first one, what happens when you go from sets to functions? And so if you remember back when I went from the set thing to the function thing, the first thing we did was to show that the function one implies the set one when you plug in indicators, right? So what I want to do now to explain what this functional statement means, I'm going to go the other way and show you that actually you can prove the inequality about functions from the inequality about sets in one dimension higher. Okay, so the way I'm going to do that is I'm going to assume I have a function and I'm going to define a set, right? So I've given a function from Rn to 0, 1. And I'm going to define a set which lives in Rn plus 1. And it's basically, well, it's not quite the subgraph of the function, but it's the subgraph of phi inverse composed with the function, right? So here, x is in Rn, xn plus 1 is in R. And this point is going to be in my set if xn plus 1 is smaller than phi inverse applied to f of x. I have a picture in a couple of slides. Let's work out a couple things about this set. So what's the volume of this set? Well, if this point is in the set, then what does that mean? It means xn plus 1 is smaller than phi inverse of f at x, right? The probability of this thing conditioned on x is just f of x, right? That's what phi inverse does for you. And so this is just the expectation of f. So my set, the volume of the set is the expectation of f. And it might not be, you might be able to guess by now that the noise sensitivity of this set is going to be the expectation of this thing that appeared on the left-hand side, expectation of j, f at x, f at y, basically from the same reason as before, right? What does it mean for x to be in the set and y to be in the set? Well, xn plus 1 has to be smaller than this, and yn plus 1 has to be smaller than that. And now if I condition on x and y, then this was just the definition of j. So that's why j is defined like that. And so you'll see that this functional inequality really is just a set inequality, but boosted up one dimension and yeah. Okay, so hopefully that explains the first mystery, which is why this why going from sets to functions is not so unreasonable. Okay, right. So I just have this little extra thing. So let's prove the functional inequality from the set inequality, right? So here's the thing that was on the left of the functional inequality, and I said that that was just the noise sensitivity of my set A sub f by the set inequality that's smaller than the noise sensitivity of a half space with the same volume. And then by what's above, this is just equal to this, right? So here I have the functional inequality from the set inequality. Okay. Now the second mystery is, now that I have this inequality, why should I expect to define this thing in terms of t and differentiate, and it should be non-negative? Okay, so let's look at, well, we have this way of viewing the functional inequality in terms of the noise sensitivity of sets. So let's see what happens to those sets when I apply p sub t. So I just picked some function here, and here's the set A sub f. Right? And now when I start applying p sub t, so here's t equals 0.01, and t equals 0.02, and as you make it bigger, then the set gets smoother and smoother and flattens out, and it goes to a constant function. Right? And now when I have when my function goes to a constant function, then the set goes to a half space, right? Because it's a subgraph of a constant function. And so what's happening here is, when I look at this in terms of sets, pt is sort of smoothing out the set until it turns it into constant. And what we showed by this differentiation is that as you do this transformation, the noise stability is increasing. And it's maybe not quite so unreasonable, because you expect the noise stability to be large if there's lots of bumps. And so if you're doing a smoothing on the set, then it's, I don't know, I mean, it doesn't, this doesn't show anything, but maybe you can believe that this is a transformation that increases the noise stability.
I didn't follow on the previous slide, but were you, since you care about an L1 quantity, you can just integrate over the level set of the function according to the Gaussian measure?
No.
In the previous slide.
This one?
Yeah.
So, I'm not doing anything nearly as fancy as that here, I don't think. I'm just saying that the inequality that I wrote for the functions is really just an inequality about the subgraph of the function in one dimension higher. So there's no non-trivial level sets. My level sets are just 0 and 1, I guess, because is that? I mean, so what I'm saying is I have an inequality about this function, and what it's really like is it's just the set inequality about this set, which is the subgraph of the function. Yeah. Is that? Okay. So this idea of having this quantity that decreases as you make t is of course not our idea, and in fact the exact same p sub t was used, well, by many people, but most relevantly to us it was used by Bakker and Ledoux to prove the Gaussian isoperimetric inequality, which is actually quite related to this noise sensitivity inequality. It's sort of a limit. So it didn't come from nowhere. Okay, so I just want to tell you a little bit more about the function j. One thing that happens if you actually do the computation that I skipped is you realize that the inequality doesn't just work for our function j. It actually works for some sort of more general j's. So in particular, if j is any function which satisfies this second derivative condition, so this matrix which looks like the Hessian except it has a row on the off diagonal, this thing has to be non-negative, then you have the inequality. Okay, and this inequality works when x and y are row correlated Gaussians. So I gave this talk once before and someone said this looks a lot like Jensen's inequality. And it sort of does. But I mean negative semi-definite. Yeah, negative semi-definite. And so this point-wise, so this is a function, right? So point-wise negative semi-definite. Yeah. Okay, so Jensen's inequality, of course, would say if I got rid of the rows, right, then this means that j is concave. Right? So if I get rid of the rows, then this inequality is true for any arbitrary joint distribution of x and y. So, I don't know if this means anything, but one way to sort of look at this theorem is to say if I'm allowed to relax the constraint on the concavity of j as long as I put some constraint on the joint distribution of x and y. And it seems to be quite special that x and y have to be row correlated Gaussians. It doesn't work if you take some arbitrary distribution with correlation row. It's not true. No. For example, Booleans is not true. Oh, spherically symmetric. No, because for example, so these have to be Gaussians of unit variance. So if I take Gaussians of a different variance, then you get a similar inequality, but with a different normalization. Yeah. You can do a bit more general than Gaussians. So for example, Ledoux showed that you can take it to be some distribution of log concave things. But definitely you can't do anything you want. So there's some conditions. Okay, so one thing that I don't know is if this condition means anything, right? I mean, it's not that the function is concave, and I've never seen it before. And as far as I know, its only use is to show this inequality. So I don't know if that's interesting. One thing about our function j, the specific function that we defined, is that it's the smallest function which satisfies this inequality. I don't know if that's interesting either.
What do you mean the smallest function?
Okay, so that's a good question. So our function j had certain boundary conditions, right? I told you its value at 0, 0, 0, 1, 1, 0, and 1, 1. Right? So of all functions which satisfy this inequality and have those boundary conditions, our function is pointwise the smallest. So if I have any other function satisfying those, then our function is smaller than that pointwise.
This does not mean that the general inequality.
You mean this inequality?
Yeah.
No, I don't think so. I think you actually have to go through the proof to see that. Yeah. Because so it would be the statement that I just said would be true if the left hand side were indicators, but on the other hand, if I replace j by something that's bigger, then both sides get bigger. So yeah. Okay, so here's a plot of j, just for fun. This is when rho equals 0.1, and as you might expect from the previous slide, when I make rho to be bigger, then this gets more and more like a concave function. Yeah. Question?
So, does the inequality work? Gaussian still.
So what Ledoux showed is that you can have so you need it to be it can't be any Markov operator, it has to be a diffusion, first of all. If it's a diffusion and it satisfies this, so I don't think the eigenvalue is enough. I think it has to, there's this Bakker-Emery condition about dimension and curvature, which implies an eigenvalue gap. So if it satisfies that condition, then you get an inequality. Yeah. So that's how I said something about log concave things a bit before. So that's how you get log concave distributions. Okay, so way back at the beginning of the talk, I said that our proof tells you about the equality and near equality cases. So I want to say how that happens. Right. So here's the claim that if f is the indicator of some set and I have equality in my inequality, then A should be a half space. Right. So this was what came out from the proof of the other thing. I had this thing that depends on t, and I differentiated it, and I claimed that you get this formula. Okay. So, and then these are okay. These weren't important before, but they're going to be important now. Vt and Wt in the formula are given by phi inverse composed with Pt. Okay, so now remember this equality is basically saying that this thing at t equals 0 equals this thing at t equals infinity. Now the only way that could happen is if the derivative is always 0. Okay, so if I have equality, then my derivative has to be 0. Well, everything on the right hand side is strictly positive. This is strictly positive, except for this, right? This thing can be 0. So if I have equality, this thing has to be 0 almost surely for every t, right? So fix a t, this thing has to be 0 almost surely, so grad vt of x is grad wt of y almost surely. And now the thing about x and y is that conditioned on x, y is fully supported. So if this thing is, or if these things are equal to each other, then they have to both be almost surely equal to a constant. Okay, so grad vt is a constant. That means that vt is linear, right? Vt is linear means that pt of f is phi composed with something linear. Pt of f is phi composed with something linear. And now what you do is you take t to go to 0, right? And if you think about phi composed with a linear function, the only way that I can get this thing to approach an indicator function is if that indicator function is the indicator of a half space, right? Because half space is a linear threshold. And so that implies that if f is the indicator of something, then A is a half space. So I might just mention, right, I don't have to put this condition that f is an indicator of something, right? I could ask, what are the equality cases of this inequality just for functions? And the answer is that you have equality if and only if f is phi composed with a linear function. And then half spaces are just a limiting case of that. Okay? Now, the last thing that I want to do today is show you this other piece. So I claimed earlier on that if f is an indicator, and I have almost equality in this inequality, then A should be close to a half space. And this is sort of like the most technical part, and I'm not really going to go into it. I just want to sort of give you a flavor. So this is the fundamental theorem of calculus, right? Something at infinity minus something at 0 is the integral of the derivative. And now the point is that for the equality case, I said that this thing has to be 0 for all t, and then these two things have to be linear and equal to each other. Well, so the first thing that we have to do is get a quantitative version of this, right? So if this thing is small, then for all t, these things are almost linear, and if these things are almost linear, then pt of f is almost a function of this form, right? And you have to quantify that in terms of delta. And then the next thing that you have to do is show that if pt is almost a function of this form, then f is almost a function of that form, right? And now the problem with the second lemma is that it's not actually true. And the reason it's not true is that pt is a smoothing operator. And so f can have lots of local stuff that disappears immediately if it's very bumpy. And so you can't actually prove this statement because it's not true, but you can do sort of special versions of it. So for example, if you include the extra information that f has good noise sensitivity, then this statement is true. But yeah, maybe let's not go into that now. So that's all. Thanks.
Earlier, this result, the stability version, was known with dependence on the dimension. Right?
No. So there was So I think our result was the first time this thing had been studied before. There's a limiting case way back at the beginning. Okay. There's a limiting case of this inequality. So I sort of mentioned it. The limiting case is the Gaussian isoperimetric inequality. And so for the Gaussian isoperimetric inequality, the history was a little bit different. So it was shown by Cianchi, Fusco, Maggi, Bertelli that if you have a small deficit, then you get something like this with a dimension-dependent constant and the square root of delta. Right, and so the history of that was that. So after that, Elkanon and I showed that you can get rid of the dimension-dependent constant, but you get something that's logarithmic in delta instead of polynomial, and then. No, I think. So what we had was like 1 over square root, 1 over log to the 6th 1 over delta, or something like that. So I think that's right. When delta goes to 0, sorry, yeah. 1 over log 1 over delta to some power. Yeah. So going to 0 when delta goes to 0, but very slowly. Right. And so then that was it was related to this work in the sense that we were studying the sort of same semigroup and the same general arguments, but it doesn't actually tell you anything either way. And then one thing about this result that was a little unsatisfying is that without, so like I said, the isoperimetric inequality is a limit of this as rho tends to 1. If you don't get the right dependence in rho here, you don't get the Gaussian result out of this result. And we could only get the right dependence in rho for sets of measure half for some technical reasons. And one nice thing about this result by Eldon is that he has the right dependence on rho, and so now you actually get a robustness statement for the isoperimetric inequality with no dimension, with a constant independent of the dimension and the correct exponent on delta. So now the question is whether you can keep that dimension independence and get rid of the square root log.
Is Eldon's proof also based on the same argument for this?
I'm not. So it's not immediately the same argument. I'm not, to be honest, quite sure yet how they're related.
So does he use this increasing property that the j function is increasing with respect to the p?
So he doesn't mention the function j.
Okay.
So he has his argument is based on stochastic calculus. So he studies a sort of martingale. I think it might be related because, I mean, if you look at what our semigroup is doing, there's some stochastic calculus in there too, right? We just sort of didn't write it in that form, and his proof is not an immediate rewriting of our proof in that form, but maybe there's a connection. Yeah. There is one nice idea that he had, which you can apply immediately to our proof, which is that it turns out that studying the measure of the symmetric difference is not a very nice thing to do. For this reason that when you apply PT, it smooths things out, and the measure of the symmetric difference can become wildly different. It turns out that there's a different metric which is quite nice to use, which is the distance between the center of mass of a set and its closest half space. And that sort of makes, right, yeah.
Can you deal with other correlation structure than the one you did?
Well, if there's two Gaussians, then there's no other correlation. Oh, you mean not having identity here? Or?
Yeah, for example.
I'm not sure. So if you don't have the identity, I'm not sure. If you have the identity and you have two Gaussians, then this is the only correlation structure, unless you turn rho negative, and then if you turn rho negative, then the inequality reverses, but we can still handle that.
But if you have like half of positive and half of negative or something.
Well, for this to be, I mean, this has to be symmetric, right? So for two variables, there's nothing else, right? So you could ask for more variables, right? What if I have x1, x2, x3, and then I have a 3n by 3n matrix here? And then we know a couple of cases. So for three variables, if all of these things, if all of the coefficients here are non-negative, then the result is still true, that half spaces maximize the noise stability. On the other hand, if I take the inverse of this matrix and all of the off-diagonal entries are non-positive, then it's also true. So the non-negative one is due to me, and the non-positive one is due to Mossel and Isaacson. If they're mixed, then I don't know.
But in general, I mean, sometimes just the fact that if you have, say, in one coordinate there's correlation rho, and in the other one there's a smaller correlation.
Yes.
Then you can just think about the smaller correlation as applying a function on the weaker correlation as applying a function on the stronger correlation. So there's in fact a family of inequalities like that that are weaker, that have immediate consequence, just by applying some Markov operator in between. So this is sort of the extreme case, but you get the sort of a convex family of inequality that you immediately get by applying this Markov operator.
But there are also some cases when you have multiple Gaussians where it's not true that that half spaces. I mean, so if you're allowed to take different sets here instead of the same set A, right? You're allowed to take different sets, and what I said here is that the best thing to do is to take parallel half spaces. Now you can actually, if you take this to be a big matrix with many Gaussians here, and you take some to be positive and some to be negative, then it might be the case that the best thing to do is to have half spaces which are not parallel. But I mean, I know that sort of by example, but I don't know what the best configuration is. Yeah.
So Eldon's proof only works for positive row, correct? So you still have that advantage over him, right?
I think that's correct. Yeah.
Yeah, I think so. Yeah. Yeah.
So how involved is the structure part to decode a half space from this deficit?
To decode a half space from the
So
deficit.
you want to prove that if you're close to J, optimal J, then you have that.
Okay.
Is it scalar or is it something more?
So what we did. Okay. So we have this expression, right? And now the point is that I claim that this thing has to be close to linear for all t. So what you can do to find a half space is you take t equals 1, and you take the best linear approximation to this function, by which I mean the L2 approximation. So I just take this guy, I look at its expectation, and I take the linear function with that slope, and then I take PT inverse of that, and I get my half space. So I mean, it's sort of fairly explicit, but maybe you wouldn't want to actually do it.